All right, let's go to number 12. Suppose that one-way commuting distance of workers at a large company is normally distributed with a mean of 21 miles. Remember, the mean is always in the middle of normal distribution, and a standard deviation of 5 miles. What is the z-score if you commute 16 miles to the office every day? Right? So the question is, if you have distribution that it has a mean of 21 and the standard deviation of 5, what is the z-score or z-value of 16? Okay. Now notice here, I mean, the formula is this. Okay, the formula is z is equal to the number that you're concerned with, which is 16. In this case, minus, it's x minus mu, the mean. Okay, so it's the difference between the value x and the mean value divided by sigma, which is the standard deviation. It's 16 minus 21, which is negative 5, divided by 5 is negative 1. This is the answer to the question. Okay, now that's fine. And you can go on to the next one if you like, but think about what it really means. Okay, so 21 is the average, the mean, right? And the standard deviation is 5. And the z-score is really the answer to this question. How many standard deviations above the mean x is? Okay, so x is 16, right? In this case, x is 16. 16 is how many standard deviations above or below the mean, right? And the answer, well, clearly 16 is 5 below 21, and 5 is the standard deviation. So clearly 16 is 1 standard deviation below the mean, right? And that's why it's negative 1. That's all this means. Okay, so you could have answered this without actually doing all the calculations if you just knew what the z-score means, okay? Because it's clearly 16, which is 5 below 21, is 1 standard deviation below the mean. All right, number 13. If you flip a fair coin 3 times, what is the probability you get at all tails? Okay, and the answer is 1 over 8. And that's pretty simple. And best way, I think, in this case, to come up with an answer is to come up with this answer, 1/8, is to list all the possible outcomes. Okay, in this case, you have 3 coins, right? And so look at this thing called a tree diagram. The first one could be heads or tails. Second one could also be heads or tails, independent of the first outcome, and so on. And so you basically have, let's go ahead and fill this, HT, 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 HT. Right? And if you follow all of these branches, you come up with your 8 outcomes, HHH, HHT, and so on. And I try to, and it's a good idea to write this in a dictionary order, lexicographical order, alphabetical order. And you can tell out of these 8 outcomes, all tails only happens once. That's why it's 1/8. How about at least 2 tails? If you look at all these 8 things, 8 outcomes, at least 2 tails happens here, 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 and including all tails, because 3 tails means at least 2 tails. So that's 4 out of 8. And the 4 out of 8 is also equal to 1/2. Okay, there are, if the numbers become really big, like if you have 10 coins, it will be much more difficult. Okay, there are ways to count these complicated probabilities, but we will not get into this. We'll stay with small numbers. Number 14, suppose that you are to choose 3 club members out of 6. Okay, so you have 6 students and you're supposed to pick 3 club members. How many ways can you do that? I ask 2 questions first. Is repetition allowed, and is the order important? Okay, in this case, you are to choose 3 club members, 3 different club members. That's sort of implicit because you can't choose one person 3 times and call that person 3 club members, right? So it's implicit, and it's pretty clear that repetition is not allowed. The order is not important because you're just choosing club members. Okay, if you pick these people, let's say Adam and Bev and Carol or something. You pick them in this order, ABC or BCA or CAB, it doesn't matter. The result is still the same 3 club members, right? So the order is not important, repetition is not allowed, and so this is a combinations problem. And so the way you think about this, I mean, if you know the formula, it's 654 times divided by 321, you get 20 as your answer. But if you forget that, or if you can't think about this, there is a logical way to think about this. Okay. Remember, if the order were important, okay, and you have 6 students to choose from, so you have 6 ways to choose the first one, and then once one person is chosen, you have 5 left from whom to choose the second person, and then once 2 people have been chosen, you have 4 to choose the third person from. Okay, so there are this many ways, and this will be 120 ways to choose 3 people in different orders. Okay, if the order were important, but remember the order is not important. Okay, and so that means ABC and BCA and ACB and CAB and all those permutations of these 3 people are counted well, once, right? It should be counted once. But if you think of these 3 people, there are 6 different ways to write them in different order. Okay, and that's because you have 3 to choose the first one, and then 2 to choose the second one, 1 to choose the third one. So then so you can write down all of these 6 permutations. If you are to choose A, B, C in different orders, how many different orders can you choose? Can you have to have the same group of members? That's A, B, C, A, C, B. I'm using the alphabetical order again. B, A, C, B, C, A, C, A, B, and C, B, A. 1, 2, 3, 4, 5, 6. Okay, and so when we count it in this way, to count the number of permutations, how many ways can you choose 6 people in 3 people out of 6 if the order were important? There are 120 ways, but they come in groups of 6. You have written the same combination 6 times if the order when the different order arrangements were made. So you have to divide this big number by 6, and that's where this calculation is coming from, right? So it's 6 times 5 times 4 divided by 3 times 2 times 1. And of course, this is 6, and this can cancel, and the answer happens to be 20. Number 15, suppose that you are to choose a president, a vice president, and a secretary out of 6 students. Look at that. This time, you are to pick 3 people out of 6, just like number 14. But the order is clearly important, because if you choose A for the president and B for the vice president and C for the secretary, that would be different from choosing A as the president and C as the vice president and D as the secretary. So the order is now important, relevant. Okay, so 6 ways to choose the president, 5 to choose the vice president once the president has been picked, and then 4 to choose the third person secretary once the president and the VP have been chosen. So you just multiply them out, you get 120 as your answer. Typically speaking, this is the number of permutations of 3 out of 6. And the number of permutations is often very much larger than the number of combinations. All right, number 16. Every motorcycle license plate is supposed to have 3. This is not the same. This is not true in California, but it may be true in other states. Every plate has 3 alphabet letters followed by 2 digits. Okay, so for instance, AGP43 would be a license plate. How many license plates are available? You have 20. So the question here is, of course, the order is relevant, important, because ABC97 is a different plate than CBA 79, for instance. Okay, so the order is definitely important, and the repetition is allowed because you can have AAA 11, for instance. Okay, so you have 26 ways to pick the first, and regardless of this, you can still pick A here. So you can have 26 choices here, 26 choices here, because there are 26 letters in our alphabet. And then you have 10 digits to choose from for this and 10 to choose from here. By the way, this number is not 9. If you count the digits from 1 through 9, of course, that's 9 digits. But remember, you can use a 0. So you have 10 choices here and 10 choices here. You multiply 26 times 26 times 26 times 10 times 10. And the answer is 1.75 6 million, or 1,757,600 license plates are possible. Okay, number 17. If you have the situation that your friend roll a die, if your friend rolls a die, and if you win, no, let's say if you get a 6, you win $8. If you don't get a 6, if you get anything else, 1, 2, 3, 4, or 5, then you lose $2. What is the expected value? All right, the question is, how much do you expect to win each time you play this game? All right. Now, because you are talking about a die that has 6 outcomes, it's good to think of some big number that is a multiple of 6. I wouldn't try with 1,000 because 1,000 cannot be divided by 6, right? So try maybe 600 times. That's a big, large number, clearly a multiple of 6, okay? And the reason you do this is because you know, and you're theoretically, you're saying 1 out of 6 probability exists for you to win each game, right? Why 1 out of 6? Because 6 is one of the outcomes. One of the 6 outcomes. If you get 1, 2, 3, 4, or 5, that's 5 out of 6 chances of losing. Then you lose $2. Okay, so if you play the 600 times, theoretically you win 1/6 of these times, which is 100 of them. Right. So in other words, if you play this 600 times, you expect to win 100 times and lose 500 times. Every time you win, you get $8. So after 600 games, times of playing, you get $800 in winnings. But at the same time, because you lose 500 times and you lose $2 each of those 500 times, you will be losing $1,000. So after 600 times of playing this game, you will be gaining 800, but losing 1,000. So that's a loss of $200 for the 600 times you play this game. So how much do you expect to win each time you play? Well, you take a $200 loss and divide it by 600, and that's negative 1/3, which is negative 1/3 of a dollar. That's a 33 cents loss. Okay, so you can say the expected value is negative 33 cents, meaning that every time you play this game, you will be expected to lose 33 cents. Okay, hopefully that is clear. Okay, so let's go to the next problem, which is number 18. Okay, number 18, going to chapter 6. What kind of growth is seen in the frequency of sound, the musical notes, right? And so remember, this is the doubling thing, right? The frequency doubles every octave, and every octave consists of 12 half steps. But anytime a doubling is included in your growth, that is exponential, right? And so the answer is it is exponential growth. And you remember that magic number to control all our music or Western musical scales is 5.946%. Every time you go to the next half step up, from C to C sharp or C sharp to D or something, the frequency increases by about 5.946%. And that way, every time you go to the go up an octave, the frequency doubles. Okay, this is that number that controls all of these piano keys. Number 19, based on the Richter scale, compare the magnitude 4.0 earthquake with a magnitude 1.5 earthquake. Okay, remember how you compare them? You can do subtraction here. You don't divide 4.0 and you don't do 4 minus 1.5 because that 3.5, 2.5 is not the answer. Well, actually you do the subtraction, but you don't divide, okay? You don't divide 4 by 1.5 to compare because these are logarithmic numbers, right? So what you have to do is remember 4.0 means that the magnitude is 10 to the 4th, 4.0, 10 to the 4th power, which is 10,000. Remember, it's 10,000 times that number we call mu naught, which is the reference number, a very, very small amount of energy. That would cause us very, very minor earthquake that will be unnoticeable by humans. But there is that reference number that's fixed. And this 4.0 earthquake means that the energy released by this earthquake is 10,000 times that mu naught. 1.5 this is 10 to the 1.5. So the answer is really, it's going to be 10 to the power of the difference. Okay, so find the difference between 4.0 and 1.5, that's 2.5. And the answer is 10 to the 2.5. Okay, this is the key. You have to raise 10 to the number, which is the difference between these two magnitude values or two Richter scale numbers. And 10 raised to the 2.5, you can do this on your calculator like this, or in some calculators, you enter this and get your answer, which is 316 times. Okay, so it may not sound like a big difference between 4.5 and 4.10 and 1.5, but it turns out that the 4.0 earthquake is, or released the an energy which is over 300 times as much as the energy released by a 1.5 earthquake. Right? And what is log of 1,000? The answer is 3, okay? And again, the answer is 3, not 10 to the third, okay? Because 10 to the third is 1,000. The answer to this question, what is the log of 1,000, is 3, okay? Not 10 to the third, not log of 3, okay? It's just number 3. And that's because 10 to the third is 1,000. Remember, this number, log of 1,000, is asking 10 to what number is 1,000? Okay, and so the answer is 3. All right, let's go to number 21. What type of states does Jefferson's method generally favor? And the answer is Jefferson's method, if you remember from chapter 8, tends to, not always, but tends to favor large states, whereas Hamilton's method tends to favor smaller states. And that's because of the way the decimal portion of the quota behaves. All right, so let's do number 22, and then we'll stop the part 2, and then we go to part 3. What is a Condorcet winner? Well, when you have multiple people running in an election, or multiple candidates running for an election, in an election, if one candidate beats or is preferred over every other candidate in one-on-one or pairwise comparison, that candidate is called the Condorcet winner of the election, okay? And under the Condorcet method of election, the Condorcet winner, if that person exists, will be declared the winner, okay? So if you have A, B, C, if A is preferred over B, and if A is preferred over C, then A would be called the Condorcet winner. Sometimes a Condorcet winner does not exist in an election. For instance, it's possible for these three people to have a situation where A is preferred over B, B is preferred over C, but C is preferred over A. And in that case, you have a little cycle or circle, and there is no Condorcet winner. Okay, so before you go to 23, let's take a break, and then 23 will be the first problem that we will address in part 3.